Is going to be a brief introduction to something called inverses, which is actually something we've been using for a very, very long time. A kind of formal definition, if a relation includes the point xy, then the point yx will be included in the inverse of that relation, which sounds more complicated than it really is. All that means is that if you've got a function f, let's just look at f for the moment. So we've got a relation there. Not even going to call it a function yet. It's a relation. There are three coordinates, three x values and y values that go with them. The inverse of that, which we write using this symbol here, and we read that symbol as f inverse, is going to be made up of the three coordinates that match up with the three coordinates in f. It's just that in each of the three new coordinates, or the three coordinates on the inverse, we have reverse switched the x and the y. Remember, x is an input, y is an output. So in the original function, when 3 is an input, 5 is an output, in the inverse of that function, it's the other way around. We'll see that in tables all the time also, where you can, I'll use the same 3 points here in the table. This coordinates of f were 3, 5, -3, 2, and 4, 1. So the inverse is, if we take the x and the y and we just switch them around, that would be 5, 3. And if we take -3, 2 and switch it around, that's 2, -3. What I've done in the table is the exact same thing as what I showed up here, just two ways of looking at a relation. Okay, nothing fancy going on here. One other point though, looking at an example here. Here's another function, call this one g of x, 702940. It is a perfectly lovely relation, and it is also a function. Remember back to when we started the year, we said that a function is any relation where every x value, has its own y value. Just one y value. So each of the three x values have a y value that go with it. So this is a function. Its inverse, on the other hand, would contain the points 0, 7, 9, 2, and 0, 4. Notice that g inverse is not a function. Doesn't mean there's anything wrong with it. But when I tell you the input into g inverse is 0, you would say to me, okay, but I don't know what the output is because it could be 7 or it could be 4. Again, not a problem. There's nothing wrong with an inverse that's not a function. It's just not a function. And if we think about it, what type of functions will have inverses that are also functions? Well, there's a name for a function where not only does every x value have only one y value, but every y value has only one x value. That's what we called a one-to-one function. So one-to-one functions, like straight lines, have inverses that are functions. Other functions that are not one-to-one, like parabolas, don't. Okay, so the takeaway so far is that the inverse of a function is when you switch the input and the output, switch the x and the y. We'll take a look at some very sort of algebraic way of looking at this. Give you a couple of functions and we'll find their inverses. So here, f of x is 4x minus 20. In order to find the inverse of that, there are a few steps we're going to take. Number one is to, the best word to use here is invert, which doesn't really help because we're describing an inverse, but okay. Invert, or switch, the x and y. Remember that f of x is a way of saying y, so I'm going to switch that around and make that be my x and turn the x from 4x into a y. So x is equal to 4y minus 20. This y value is f of x, this y value is f inverse. I could use f inverse there as notation if you wanted, but I think that gets a little ugly and hard to read, so I'll stick with y. Okay. And the next thing we're going to do is solve for y. So in this case, it's not that hard. I'm going to get y by itself by adding 20 to both sides. and then dividing both sides by 4. And that's my inverse. I do want you to write it as f inverse when you're done. So my final answer will be that f inverse of x is equal to x over 4 plus 5. And those are your steps. The very first step is when you're actually doing the inversing. You actually switch the x and the y. Everything after that is just because we like to get y by itself. So that's what we'll do. That way we could use the function notation. So we'll do that for number 4 also here. G of x is x squared minus 9. So we'll switch the x and the y, make that x equals y squared minus 9. One really important thing to point out here is that the squared stays where it was. If in the original function, g of x, that squared is on the x, then when we take the inverse of g of x, the square will be on the y. The square stayed where it was, it's just the variables x and y switch places. So now when we solve for y, we'll just have one extra step in this solving. I can get the y squared by itself, but of course we know what to do now. Because we've solved plenty of quadratics, we know we have y squared, so if we take the square root of that, we'll get the y by itself. But you may have recognized that there's going to be a catch here. Because I'm taking the square root of both sides, we remember from our lesson unit on quadratics that I have to take the plus or minus square root. So what's interesting here is that our inverse of g is not actually a function, because an input can't be both a positive value and a negative value at the same time. So what we'll do here is there are a couple of things we could do. One is we could just leave it the way it is and say the inverse of g is not a function. It is that y is equal to the plus or minus square root of x plus 9. Honestly, normally, I'm fine with that. What I will not do is I will not put that into function notation. Cannot do that. One thing that you'll learn about in a pre-calc class is some things you can do is control the domain of the original function. You can say, if this x from the original function, from g of x, is only positive, then we could look at only the positive value here. But that's a little bit beyond what we need to do. We're not going to worry about that. For us, you can leave it like this, just don't turn it into function notation. Because I don't want you to write it as f inverse if f inverse is not a function. I know I've spent a bunch of time already talking about function, not a function. I don't want you to stress over that. It is not a big deal with what we're doing. The truth is, the reason why we're talking about inverses now is because we're going to talk about a very particular inverse function in the next couple of lessons. And it's the inverse of a one-to-one function, which means we're not going to have to worry about this whole function, not a function thing for very long. So don't stress it too much. Okay, a couple of other points to make about functions. Number one is an important way to think about it. This is the same example that we started with. But if you remember, we had this symbol earlier in the year called a composition. It's when we take the result of one function and plug it into the other function. So we're going to find f inverse of f of 3, or if you want to write it this way, f inverse of negative 3. Well, f of negative 3 we know is 2. And f inverse of 2 is negative 3. And so I want you to notice that when we took a negative 3 and plugged it into f, we got a 2. And when we took that 2 and plugged it into f inverse, we got the same negative 3. Not a coincidence. This is the whole point of inverse functions. The whole point of an inverse function is we go back to our function machine diagrams from earlier, an inverse function is a machine that you can use to undo whatever you just did with f. So if f took x and turns it into y, f inverse is going to turn it back. That's the whole point of an inverse function. This will come up a lot later in the year. A classic example of inverse functions are x squared and the square root of x. If you take a number and square it, and then take its square root, you will come right back to where you started. The square of 5 is 25. The square root of 25 is 5. That's literally the whole point of square root, is to be the inverse of a square. Okay. One other thing to note, it's worth pointing out, there's a graphic element to what we're doing here too. I'm not going to focus on this very much, but it's worth pointing out. Here is x squared minus 9. That's the red one. Hopefully you recognize that parabola. And the green graph is both the positive and the negative square root of x plus 9. Notice how it's moved backwards, right? The square root of x plus 9, moved backwards 9, and then it has the square root graph. And then the negative version will just be the upside down. What I want you to notice about this is there is important symmetry here. Hopefully you recognize that line that I drew. Didn't draw it exactly perfectly, but close enough. That is the line y equals x. And I want you to notice that there's symmetry about the line y equals x. That's going to be helpful for us when we take a look at inverse functions later on. It makes sense that there's symmetry about the line y equals x, because the whole point of an inverse is we switch the y and the x. Okay, that is the main element of what I wanted to cover in this lesson. However, we'll look at that in class tomorrow. I do want to look at a couple of other examples. These are trickier examples of how you find inverse functions. We will have time to look at examples like this in class, so if you have trouble with these, it's not the end of the world. We'll take a quick look at two of these. Find the inverse of y equals, or f of x equals x squared minus 8x plus 5. So again, the first thing we're going to do is, switch that around. X equals y squared minus 8y plus 5. And how am I going to get the y by itself when there are two different y's? I'll give you a second to think. Remember back to what we've done a bunch of times this year. And if you're saying to yourself, oh, that's a quadratic. I know how to solve quadratics. I'll complete the square. Well, that's correct. We'll complete the square here. So I'll move the 5 over. And then complete the square. So I'll have to add 16 here. I'll add 16 here too. So x minus 11 is equal to, the reason why I added the 16 is to make it exactly y minus 4 squared. And so here's where the square root will come in. And when we complete solving for y, we'll have y is equal to 4 plus or minus the square root of x minus 11. I'm going to leave it like that again because I can't put it into function notation because that's not a function. Okay, we'll try the next one, which is another fun little trick here. We'll start by switching the x and the y. So y, instead of g of x equals x squared, 2x minus 3 over x plus 4, x equals 2y minus 3 over y plus 4. And again, we'll have to dig back into our knowledge from this year, think of some of the tools we've picked up over the course of the year, recognize that, like, hey, this is what we would call a rational equation because there's what we're trying to solve for, that y is in the denominator. And we know very well that when there's a rational equation, we'll multiply both sides by the denominator to cancel it out. And so now I'll have x times y plus 4 equals 2y minus 3. Nothing else there because the y plus 4's have canceled out. And now I need to get y by itself, and this is a great sort of helpful trick to help us in all sorts of situations in math. If this looks weird to you, x times y plus 4 equals 2y minus 3, just think to yourself, what would you do if it was a lot easier? We've seen this trick before. What's making this look hard is that there's this second variable or second unknown there. I guess in this case it's a variable. We're trying to solve for y, but there's an x. Well, let's pretend it wasn't an x. Let's pretend it was just a 5. What would you do if this said 5 times y plus 4 equals 2y minus 3? And you want to get the two y's to work together? Well, you would need to break through those parentheses and distribute that 5. So that's what I'm going to do with the x. I will break through, distribute that x. xy plus 4x equals 2y minus 3. And the point of doing that was that I could get my y out of the parentheses, so that way I can move it over. Well, now the y is out of the parentheses. Let's move it over. Because in the problem without the x, if it was easier, what we would do is say, all right, these y's need to work together. So let me move this y over to the other side. So I'll do that here too. It doesn't matter which side you move it to, so you can decide which one you want. I will move the 2y over. While I'm at it, just like I would move the 20 over from this side, I will move the 4x over. Notice how it's not a like term, so I didn't put it underneath the 3. Okay. And so my line now is I've got xy minus 2y. They're not like terms, so I can't combine them. And I've got negative 3 minus 4x, which are also not like terms, so I can't combine them. Seems like we've gone in circles, haven't gotten very far, but we're actually quite close because my job is to get y by itself. In this case, I would be able to just combine the y's and make that 3y. The whole point is so that there could be just one y. Well, I can do a similar thing here, make it so that there's only one y. The trick is to factor out that y. xy minus 2y, I'm going to factor out the y. Because now it's very easy to get the y by itself. And this one actually is in function notation. So for my final answer, I will write it in function notation. G inverse of x is equal to negative 3 minus 4x over x minus 2. And that's my final answer. If you leave it like this without the function notation, that's fine too. And the one thing I want to close with before we move on is that we started with a actually back up a step. We started here with a quadratic function and our inverse was a radical. Notice that in this one, when we start with a rational function, our inverse is also a rational function. In class, we'll take a look at some other functions that we've seen through the course of the year and figure out which kinds of functions are inverses of what other kinds of functions.